Again, let's remember the contents of this chapter. Chapter 3: Electricity, Magnetism, Electrostatics, Electric current, the rules, electric current, the theoreticals, and home installation. This section of the chapter was the basic electricity. After that, the electric motor and the electromagnetic induction, and this section was titled as Electromagnetism. The last part, which involves electronics, contains Lesson 7, the CRO, Cathode Ray Oscilloscope, Lesson 8, the circuit components, and ending the chapter with the logic gates. As we finished the 7 lessons, now approaching the end of the chapter with Lesson 8, the circuit components. Better to start with an introduction. What are the circuit components? Everything that can take place in an electric circuit is a circuit component. We already studied some of them. Familiar examples are the DC battery or power supply, the AC power supply, the ammeter, the variable resistor, the voltmeter, the lamp, the switch, and the resistor. In this lesson, we will study more circuit components that are widely used in our lives. The normally open reed switch, the normally closed reed switch, the reed relay, the electromagnetic relay, the capacitor, the diode, the thermistor, the light-dependent resistor LDR, and finally the transistor. The first circuit component is the normally open reed switch. To understand how this switch functions, let us put it in a circuit with a DC battery and a bulb. A normally open reed switch contains 2 iron reeds, specifically soft iron. The 2 iron reeds are normally separated, so the circuit is open, no current flows, and lamp is off. Now we will approach a magnet to the switch. If a magnet is approached, the reeds become magnetized by induction with the shown polarity. Due to this polarity, the reeds attract each other. The circuit closes and bulb lights. If the magnet is removed, the reeds separate again and circuit opens. The second circuit component after the normally open reed switch is the normally closed reed switch. A normally closed reed switch contains 2 iron reeds, and the third is copper, or any non-magnetic conductor. 1 iron reed and the non-magnetic reed are normally connected, so the circuit is closed, current is flowing, and lamp is on. If a magnet is approached, the reeds become magnetized by induction with the shown polarity. The reeds attract each other, circuit opens, and bulb becomes off. Another switch is the reed relay. The reed relay works like the normally open reed switch. 2 reeds are made of soft iron, but in this case the bar magnet is replaced by a separate electromagnet circuit made of a coil of many turnings, a supply, and a switch. Now we have 2 separate circuits, the main circuit of the bulb, and this will be controlled by the electromagnet circuit. Note that there is no any electrical connection between the 2 circuits. If we close switch S1, current flows in the coil and magnetizes the iron reeds. Iron reeds attract, current flows in the main circuit, and the bulb will light. By this way we can control a big circuit by another smaller one, which acts as a switch for the bigger circuit. Another way to control a main big circuit from a smaller switch circuit other than the reed relay is the electromagnetic relay. What you see now is the main circuit to be controlled. It is made of a cell and a bulb. This circuit is open and the bulb is off. A smaller circuit will act as a switch and controls its on and off. It contains an electromagnet made of iron rod and a coil. This is an armature which is also made of soft iron to respond easily to the electromagnet. The armature rotates easily about the shown pivot. If we close switch S1, current flows in the coil and the iron rod is magnetized. When the iron rod becomes magnetized, it becomes able to attract the armature in the direction shown by the black arrow. When the armature is attracted, it rotates about the pivot and closes the open contact of the bigger circuit. The armature attracts to the rod and closes the contacts. This was another idea to control a bigger circuit from a smaller one, which acts as a switch circuit. This was the electromagnetic relay. After finishing the electromagnetic relay, it's time to discuss the fifth circuit component in the syllabus, which is the capacitor. The function of the capacitor differs from previous components. It is not a switch. This shows real capacitors. The capacitor from inside is made of two plates. Between the two plates is an insulating material named the dielectric. This is the circuit symbol of the capacitor, made of two metal sheets and the dielectric material. The meaning and explanation of the word dielectric is out of our syllabus. Let's see what will the capacitor do. The capacitor's main function is to store electric energy, and it causes delay. In the circuit shown, the capacitor will delay switching off the lamp. The capacitor now is in parallel with both the cell and the lamp. Close switch S1. The cell is 6 volts, and it is the main electric energy supply to the bulb. The current will flow in both the capacitor and the bulb. The bulb will light, and the capacitor will charge and store electric energy until the potential difference across it becomes 6 volts, which is the full voltage of the battery. Current will flow in the lamp. Capacitor will charge till it reaches the full voltage of the DC battery. Once the capacitor reaches 6 volts, which is the maximum possible voltage in the circuit, the current stops flowing in through the capacitor. When capacitor is fully charged, the current stops flowing through it. Now open S1. This means the battery is off. Even though the circuit is open, the bulb is still on, because the bulb now will consume the electric energy stored by the capacitor. Switch S1 is now open. The lamp will light with the stored energy in the capacitor until it's completely used up. As you can see, the brightness of the bulb decreases until the electric energy is completely used up. The capacitor caused a delay in the lamp switch off. Now let's see what will happen if the capacitor is connected in series to the bulb. Close switch S1. The current will flow in both the capacitor and the bulb. Current initially flows. The capacitor will start charging, and as it charges, the current decreases. Capacitor charges and current decreases. When capacitor is fully charged, current stops and lamp becomes off, because now the capacitor has a voltage of 6 volts, which opposes the 6 volts of the battery, and the current is blocked. After the capacitor, it's time to circuit component number 6, the diode. Diode and circuits. This is the symbol of the diode. A triangle represents the head of an arrow, and a line representing the block. If the current in the circuit is flowing in the direction of the triangular arrow, this is named forward bias. But if the current in your circuit is flowing in the direction opposing the block line, this is named reverse bias. In the forward bias, the current is allowed to flow, but in the reverse bias, current will be blocked. That is why we can say that the diode is a circuit component that allows the passage of current in one direction, but not the opposite. Let's have more explanation. Normally, regardless the direction of the battery, the flow of current causes the bulb to light. In the circuit shown, a battery is connected to a bulb, and the bulb lights as the current flows. In the second circuit on the right, the battery is reversed, but the bulb is still lighting, since the current flows but in the opposite direction. These two circuits show that the direction of the battery does not matter. But in the presence of a diode, the situation will be different. In this circuit, the current will flow from positive pole to negative pole of the battery. If we add a diode, we can see that the direction of the current is in the same direction of the arrow of the diode. This means forward bias, and the diode will allow current to flow. But now have a look in the circuit just appeared. The battery is reversed. This made the current opposite to the direction of the diode. This is a reverse bias. The current will be blocked by the diode, and the bulb will not light. Another example of blocking the current is reversing the diode instead of reversing the battery. In this case, also the direction of the current is opposite to the direction of the arrow of the diode. The semiconductor diode allows the passage of current in one direction, but not the opposite. As in the forward direction it has the low resistance, but in backward direction it has a very high infinity resistance. This means that the diode is a resistor that depends on the direction of the current. So if the current is in the forward direction, its resistance will be very small. But if the current is in the backward direction, its resistance will be very large enough to block the current. It is made of a semiconductor like silicon or germanium. Diode and increasing voltage. We will study first the forward bias. This circuit shows a forward bias connection, so the bulb will light. If we increase the voltage by adding one more cell, the current will increase and the brightness of the bulb will increase. Adding one more cell will cause the bulb to be more and more bright. So in the forward connection, it's clear that if the voltage is increased, the current will also increase. Now let's see the reverse connection or reverse bias. As you can see, no current will flow because the direction of the current will face the blocking side of the diode. What if we add one more cell? No change and no current flows. Even if we add more and more cells, no current is allowed to flow in the reverse bias. So we can conclude that increasing the voltage on the reverse bias connection makes no use. We can draw the IV graph between voltage and current to describe the relationship as seen. The graph shows the relationship between the voltage and the current in both reverse and forward connection. You can see that in the reverse bias region, the current is always zero, but in the forward bias region, as voltage increases, the current will increase. Another thing to notice, even in the forward connection there is nearly no current until the voltage exceeds 0.6 volts. So a minimum voltage for the diode to work is 0.6 volts. The next part is the diode and the AC voltage. Let's first remember what is an AC. AC is explained as the current that flows in both directions, having positive and negative values. This is a representation of AC on the cathode ray oscilloscope. Now let's add a diode. The diode will allow the passage of current in one direction but not the opposite. That is why it will allow one direction to pass and the opposite current will be blocked. The current which comes with the arrow on the diode will pass, but which comes with the block will stop. Here we can say that the diode changed the AC to DC. Remember, this was the AC wave from the CRO. If the voltage is drawn by the CRO after adding the diode, This is what you will see, since one direction is allowed to flow, but the opposite will be blocked. Next part is the diode and charging DC batteries. Any battery is charged from the main supply, which is AC. But wait a minute, how can an AC supply charges a DC battery? This is because any DC battery charging circuit must contain a diode. This diode is to change the AC to DC. The battery to be charged must be connected in the circuit, so its positive is in the direction of the block of the diode. This is to avoid any current leakage from the battery during the process of charging. Importance of the diode in chargers. Number 1. The diode is used to change AC to DC. Number 2. To avoid the discharge of the battery during the charging process. Last part to study about the diodes is the light-emitting diodes, LEDs. They are not more than a normal diode that allows passage of current in one direction but not the opposite, but they have the ability to produce light in case of the forward bias, the case where current flows, and they give no light if no current or the bias is reversed. It is simply a diode that gives light when current is passing, and no light is given when current is not allowed to pass, or no current at all. After studying the diode, we have two circuit components that have some similarities: the thermistor and the LDR, the light-dependent resistor, a resistor that depends on light intensity. This shows the symbol of a real thermistor. The thermistor is a temperature sensor. It is a sensor that is sensitive to temperature changes. For any wire conductor, if temperature increases, also its resistance will increase. In any normal metallic wire, the increase in temperature causes the increase in the vibration of the atoms, causing more resistance to the flow of electrons. So the resistance increases. But for the thermistor, the case is the opposite. As temperature increases, the resistance decreases. The mechanism and explanation of how resistance of the thermistor, which is made of semiconductor materials, decreases with increasing the temperature is not included in this level. It will be discussed in A-level physics. This graph shows the resistance changes with the change in temperature. A component that is similar to the thermistor is the light-dependent resistor LDR, but it is not sensitive to temperature, it is sensitive to light. It is the light-dependent resistor that depends on light intensity. For the LDR, as light intensity increases, its resistance decreases. And this graph shows how the resistance of the LDR varies with light. That is all what we need to know about the thermistor and the LDR in this level. After we finished the thermistor and the LDR, now it's time to the last component, the transistor. Number 9. Transistors. The image shows a real transistor. It is clear that it has 3 connections. One is labeled E, and the middle is labeled B, and the third is labeled C. How to draw its symbol? You first draw a circle, and then 3 short lines as shown, and then the connections. A transistor is a small semiconductor device. It is made of semiconductor materials like silicon and germanium. A transistor is used as a switch or amplifier. We use the transistor basically as a switch, as it has many advantages over the common mechanical switches. Advantages over other switches: small, cheap, no moving parts, so less probability of being damaged, and that's why it has a long life, can switch on and off rapidly, many times in short time period. Let's go back to the symbol of the transistor and draw three connection ends. The first end is named collector. In our case in this syllabus, the collector receives the current from the external circuit. The middle end is named the base, and its function is to control the current coming from the collector. The third end is the emitter. In our case, it's the outlet of the current after passing the transistor. Our main big circuit that will be controlled is connected to the emitter and the collector. This circuit contains a cell, a mechanical switch S1, and the bulb. This circuit in the presence of the transistor has no current because the transistor is normally off. And as you see, whatever you do, making S1 on or off, no current flows because the transistor will not allow the current to flow. It is normally off. But how can we make the transistor on to allow the current flow in the circuit? The theory of the transistor claims that to make the transistor on and allow the current to flow through it between the collector and the emitter, there must be a voltage between the base and the emitter that is not less than 0.6 volts. This is the minimum value for the transistor to work. The simplest way to do this is by connecting an 0.6 volt cell between the base and the emitter. Once this happens, the transistor becomes on and allows the flow of current in the bigger circuit between collector and emitter. The current flows and the bulb lights. In a few words, we can summarize the way transistor works as follows. When the voltage VBE between base and emitter becomes greater than 0.6 volts, transistor switches on and the current flows between the collector and the emitter. Note, if VBE increases, also the current in the main circuit between collector and emitter increases. We can allow more current to flow in the big circuit by increasing the voltage between base and emitter. In this part, we will use the transistor to construct alarm circuits. Mainly, we will study the temperature alarms, like cool alarm and heat alarm. Also, we will study the light alarm, including dark alarm and light alarms. But first, let's quickly revise how transistor works. Even S1 is closed, bulb is off, and there is no current because transistor is normally off. To make it on, we need a voltage greater than 0.6 volt between the base and the emitter. The simplest way to do this is adding a battery. In this case, the transistor switches on, current flows, and bulb lights. A new idea is to get rid of the 0.6 volt cell. Let's start with the cool alarm. Between the base and the emitter, we added a thermistor instead of a cell. This thermistor is in series with a fixed resistor. Let's see how it works. But remember that the condition still applies. There must be a potential difference greater than 0.6 volt between base and emitter. Another thing to remember is the thermistor and the resistor are in series with the main battery. This means that the voltage of the battery is shared between them. The one that has the bigger resistance will acquire a bigger voltage from the battery. The transistor in our circuit is normally off. This means that this part of the circuit is neglected, since no current will pass in it. So this becomes our starting circuit. A battery with a fixed resistor and a thermistor in series. The fixed resistor and the thermistor in series will both share the voltage of the battery. Remember that this is a cool alarm. If weather becomes cold and temperature decreases, this means the resistance of the thermistor will increase. You can revise the thermistor part to know how it works. When the resistance of the thermistor increases, its share of the voltage increases. When the voltage across the thermistor exceeds 0.6 volts, in other words, the voltage across base and emitter becomes greater than 0.6 volt, so the transistor switches on and the current flows between the collector and emitter, and the bulb will light. If you have a general overview on the circuit, you find that the bulb will light when weather becomes cold, when voltage across base and emitter becomes greater than 0.6 volt, transistor switches on, and current flows between collector and emitter, lamp lights. Don't go and just wait for 3 more examples. They will make it clearer. Another example is the heat alarm. The same way of thinking, this part of the circuit can be initially neglected because transistor is normally off. In the heat alarm, these are the positions of both the thermistor and the fixed resistor. So if weather becomes hot and temperature increases, the resistance of the thermistor will decrease. You may revise the thermistor part to remember how it works, so its share of the battery voltage decreases. This automatically increases the voltage across the fixed resistor, which is placed between the base and the emitter of the transistor. When voltage across base and emitter becomes greater than 0.6 volts, the transistor switches on, the current flows between collector and emitter, and the bulb will light. If you have a general overview on the circuit, you will find that the bulb will light when weather becomes hot. When voltage across base and emitter becomes greater than 0.6 volts, transistor switches on, current flows between collector and emitter, and lamp will light, giving an alarm that weather is hot. Another example is the dark alarm. It will work if it goes dark, the same way that transistor is initially off, so we can neglect this part of the circuit. Note that here we have an LDR instead of the thermistor. When it goes dark, the light intensity decreases and the resistance of the LDR will increase. You may revise the LDR part to remember how it works. When the resistance of the LDR increases, so its share of the voltage will also increase. When the voltage across the LDR becomes greater than 0.6 volts, in other words, the voltage across base and emitter becomes greater than 0.6 volts, the transistor switches on, the current flows between the collector and emitter, and the bulb will light. You will find that the bulb will light when the surround becomes dark. One last example is the light alarm. The same way the transistor is normally off, so ignore these parts of the circuit. If light intensity increases, the resistance of the LDR will decrease, so its share of the voltage will decrease. This automatically increases the voltage across the fixed resistor, which is placed between the base and the emitter of the transistor. When voltage across base and emitter becomes greater than 0.6 volts, the transistor switches on and the current flows between collector and emitter. The bulb will light. You will find that the bulb will light when light intensity increases. When voltage across base and emitter becomes greater than 0.6 volts, transistor switches on, current flows between collector and emitter, and lamp lights. For examples to show how the transistor can be used in alarm circuits. There are many other sensors that can be used, like humidity sensor to make the humidity alarm, using the same idea.